Welcome back. So in the part 2 of this particular lecture, we will actually get into the basics of adaptive control. The part 1 was focusing more on challenges of control designer. So before we get into anything, let's actually talk about adaptive control at a very high level. What is the idea behind it and things like that. So if you recall, the linearization method essentially did something like this. If we have f x dot equals f of x, I'm going to put control here. Though we didn't discuss specifically this particular problem, and you will see now what I'm doing. This can be approximated to a system that looks like x dot equals ax plus b times u plus some higher order terms, right? Let's call them x square or something like that. Okay, and hopefully in the very close proximity of wherever we are at that particular point, this is so small that it doesn't matter. And so we can treat this as a linear system. We know how to basically design a full state feedback controller and more general techniques through output control, or for that matter sometimes dynamic control, right? We have those techniques. So the thing is, basically, if we know that technique, so can we not actually somehow keep changing this k? A keeps changing. So can I not change k so that whenever this a changes? Why does a change? Because as x change, this f of x changes, and then the derivative, the gradient, the Jacobian of that is basically going to change. So a keeps changing. So a is probably change with some parameter alpha. Alpha is like the some parameter determining the path and things like that. And then so the k alpha is basically what needs to be done. So the assumption is basically if a alpha is changing slowly, k alpha can also be changed. And this idea was used quite a bit to stabilize systems. And then in simulations they worked perfectly, and in experiments also they worked very nicely. And they had a major program to test this particular idea to fly an aircraft and things like that. And there was an unfortunate incident where they lost an aircraft along with the pilot. And these days we see many accidents, and then a lot of times those accidents happen due to human error or some other instrumentation error and things like that. The analysis of that particular project resulted in concluding that the closed loop controller that they were doing, the adaptive control, happens to be unstable. Rather, they could not prove stability, right? So that led to an entire exploration of basically techniques where we can show stability through Lyapunov functions of this adaptive technique. And then what you see here is actually the stable adaptive control technique. You won't see the general technique that was invented, which was in some sense discarded because of its inability to show stability in certain regions. So anyway, so in order to understand adaptive control, we have to go beyond, unfortunately, LaSalle theorem. I say unfortunate because it doesn't give the best results that LaSalle gives. We have to struggle a bit in terms of showing convergence and things like that. If you recall, LaSalle theorem essentially basically says that if you have a bounded trajectory, then you will end up that basically x of t will have a limit set, and then that limit set is going to be invariant, and this x is going to reach that limit set, and that limit set can be found through certain techniques using the invariance and things like that, right? All that nice things are not there in the case of systems that we are dealing with adaptive control. So we have to go with a little bit more complicated results, right? So one of the standard facts that we have come across earlier is basically if v is lower bounded and on a trajectory x, v of x of t is non-increasing, then we can say it's decreasing, let's say, loosely speaking, not strictly decreasing. That's the typical terminology we use. Then v of x is going to be v of x of t is going to be bounded. So on the trajectory v is going to be bounded. Much more, the limit is going to basically exist, right? So in fact, more general general things, basically if you have a monotonically increasing or decreasing function, or non-increasing or non-decreasing function, and if it is bounded, then you don't have a choice but to basically reach some limit, right? So let's keep that in mind. But then just because v is going to limit does not guarantee limit of t tends to infinity v dot of 0. I mean, let's look at a picture of this particular thing. So we know there is a function v of x of t that's consistently decreasing, right? Non-increasing at least. And so we know that this is going to reach a limit. It's lower bounded. So it seems this picture is saying basically at the end v dot is going to be 0. Okay, what that remark is saying, that not guaranteed, right? And I can't give you an example here because it's a quite pathological, it's very artificially constructed examples, and I would urge you to basically search Google like a monotonic function has a limit, but the derivative of the function need not be 0 or something like that. If you type it, and then you will see examples given by others, right? So, but this is a very important thing. I mean, we cannot just conclude v dot is 0, right? But something still will be true, right? Sorry, there's a typo here. This is actually an integral there. So let f be uniformly continuous, right? It's continuous, and then the epsilon delta, the delta part is not going to be dependent on where we are in terms of checking that continuity. And this integral of absolute value of f is less than infinity, then limit is going to be 0, right? So we want to somehow show this limit v dot is 0. Unfortunately, just showing that limit exists, what do you call, lower boundedness of its integral is not enough, but something more has to be true, and we'll look at some of these details. So please note that this integral of the absolute value of dt is less than infinity, then and uniform continuity guarantees that the limit is going to be 0, right? So perhaps so what we are saying is, if 0 to infinity of absolute value of dt is less than infinity, then f of t going to 0 as t tends to infinity. And suppose if this did not go to 0, let's say if it reaches some number m, okay, if it limits to some number m, then basically you can clearly see that this integral is going to be not bounded at all, because you can at some point it's very close to that number, and then basically you can integrate from that time onwards. The absolute value is going to be more than 0, and therefore you will not get this thing. On the other hand, even if it is oscillating, the same conclusion can be drawn, right? But then you'll see that you can actually construct functions which are not uniformly continuous, and in which case the limit is not going to be 0, right? But only in the case of uniform continuity we get this property, right? So as a corollary to this, it's very important, is basically if f is such that f and f dot are bounded, and again this integral 0 to infinity of the square of f is less than infinity, then limit is going to be 0, right? And so what does this mean? So if we have v such that it is upper and lower bounded by some alpha and beta times square of the norm of x, if x is such that x dot is bounded and v of x is non-increasing, then limit x goes to 0, okay? So instead of worrying about v dot being 0 and things like that, in the limit we directly can actually use this particular result, where x of t is going to go to 0 as t tends to infinity. If you recall, basically what we are trying to show, in the LaSalle case, x going to 0 came from the fact that the only invariant set in v dot equals 0, the set is actually the origin, right? Unfortunately, if we cannot show v dot is going to be 0, then we are out of that choice. So we have to have a different method of showing it. So this is the fact, right? I understand that this is probably a very dry thing, but if you can understand it, well and good. But on the other hand, it's a very powerful result. If v has these upper bounds and then v is non-increasing, The only thing that we need is x and x dot is going to be bounded and x also has to be bounded. Then the limit is going to be 0. So that brings us to the main topic, which is basically adaptive control, where we have this system x dot equals a x plus bu. Here we assume u is control input. That means we can choose whatever we want, or at least measure in this particular specific scenario. And the problem is basically identify the values of a and b based on somehow we can choose u and probably its output measurement. In this particular case, the scalar's case, x is the output. If we can measure both of them, then we should be able to measure a and b. Okay, so what that means is you have the system. By basically measuring solution of this particular thing, can we back out a and b? And then the answer turns out to be relatively straightforward, right? So if we choose the initial condition to be 0, then and then ut can be chosen to be unit impulse, then basically we can show that x of t is going to be e raised to at times b. That's part of the solutions that we looked at in the linear systems. And by just taking log on both sides and then basically pick 2 data points and solve for a and b, right? We have 2 unknowns and we need 2 equations, and then basically at 2 different times if we can measure x of t, and that's more than enough, right? So this works perfectly where we can choose the initial condition and inputs. We can put whatever we want. Though I choose in unit impulse because it keeps the equation simple, we can actually go for more complex inputs and then still do the same thing. But it has to have a system that is actually tested offline and then basically collect the data and then get the values of a and b. And then this technique can be generalized to vector systems also, where we have a and b as matrices and things like that. And this is a very standard system identification. But unfortunately, what happens if it is unstable? Basically, if you perturb with something and then suppose you don't know that the system is stable, and how will you know? We don't even know what is parameter a. And if you don't know if it is stable, when if you perturb with something, and it may actually blow up, and then that could be dangerous, right? We don't even know how far we can allow the system to go and things like that. In reality, if we can hope for basically somehow put stabilizing controller and then start measuring, but then if you don't know a, how can you stabilize? So these are the questions that were grappling people who discovered this adaptive schemes. And this scheme requires all offline, whereas can we actually identify the information is there, somehow figure out through the data that is coming out of the system when it starts running with some arbitrary u and things like that, right? So therefore we will go to a technique that does adaptive system identification, and though control is our primary desire, we will look at system identification simply because it provides some insights, and it's also one of the things that we need to understand to talk about one of the adaptive control techniques, right? So anyway, so here we'll assume basically x dot equals ax plus bu, and here again a and b are unknown. So we want an estimator model x hat dot is equal to a hat dot x hat dot x hat of t plus b hat of t times u of t, right? What does this mean? There are 2 ways of looking at it, okay? One, we are attempting to try to get to the values of a and b, but in reality we could care less about a and b, right? What we really want, why do we want a and b? So that we can predict the value of x of t, right? There's no other reason, believe me. Basically, even if you are trying to control something or understand something, it's x of t is what is needed. A and b are incidental, right? These are the models. In fact, we don't care about the model so much as if we have a technique that we can predict the state of this particular system. So therefore, instead of trying desperately to find out a and b, we'll actually figure out a shortcut where we're going to come up with an estimator, where this estimator will provide the value of x of t, and hopefully on the way it will produce the values of a and b, but perhaps not, right? So the problem of in this particular case is basically identify a strategy, identify an algorithm to achieve this limit a hat goes to a and then limit b hat goes to b. I should have stated x of t going to x of t actually, and then that's the more sensible strategy, right? So here is the first adaptive control strategy. So the the idea behind this entire adaptive control is basically, A and B are constant parameters, but I'm going to start estimating values of A and B through some other function A hat and B hat, and this A hat and B hat are going to be updated constantly, and of course not surprising that they are going to be dependent on the system that we are dealing with. Then we can show this particular fact says the estimator is going to be exactly equal to the original state in the limit, right? And a couple of other things are true. Limit of e dot a and e dot b is going to be 0, where this ea and eb are errors in the parameters of a and b, right? So let's actually look at the proof of this. Okay, so I have this x dot equals ax plus bu. The idea is I want x dot is equal to some estimator a hat of t, x of t. I'm just writing these t's so that we are clear, but I'll drop soon. Okay, so this u is same, right? The same input can be given if you can measure the input that is disturbing the system, right? So the question is basically, can I update my loss such that a hat goes to a, b hat goes to b, and x hat goes to x, right? This is a time function, these are times, but these are constants. Okay, so how do we prove this? So define ex to be x hat minus x, right? So then therefore e dot x is going to be the difference between those two, and you'll get something like a hat x hat minus a x plus b hat minus b times u. And then let's define ea to be a hat minus a plus and then eb to be b hat minus b. Okay, and then this can be written as something like a hat x hat minus ax hat plus ax hat minus ax plus eb times u, which is nothing but if you see this ea times x hat plus a times ex, okay, plus eb times u. Okay, so here we assume that a is less than 0, and then if you want to deal with a positive, then we have to do more work, and then I'm not going to consider that example. So basically what we have is e dot x is equal to a times ex plus ea times x hat plus eb times u. Okay, so I'm going to now consider a Lyapunov function that deals with ex, ea, and eb, right? So in other words, what I am trying to do is this is an equation ex. I want an equation in ea and eb, right? So I can actually design these things because those update laws are in my hand. So this is the system that we are dealing with, and this is going to be something like ex square plus ea square plus eb square with a half in front, and v dot, okay, v dot is going to be ex times ex dot plus ea times ea dot to be determined plus eb times eb dot, right? So but let's substitute for ex dot, which is nothing but a times ex plus ea times x plus eb times u plus these two things here. Okay, so I have a times ex square plus I can see that ea times ea dot plus exx plus eb times eb dot plus ex times u. Okay, So since I have choice of picking EA dot and EB dot on my own, I can choose it such a way that these two go to 0. Okay. So I will end up with B dot is equal to A times E square X less than equal to 0. Okay. So let's see, where are we now? So unfortunately, this system, if you actually look at it, you know, even after you substitute, so I'm going to write this as EX times X and EX times U, and you have this system, right? If the system didn't have any external inputs, and by the way, U is external coming, even if in the case of U equals 0, things will be still strange. But X hat is kind of an external input to this error system, right? X is an external input, so it's time varying system in that sense, right? It's not a time invariant system, so we cannot have guarantee of invariant limit sets and things like that. So that's the first difficulty. So LaSalle cannot be applied directly. So like I said, therefore V is decreasing, right? But does not guarantee V dot is 0. If V dot somehow is 0, then we could have shown that Ex is less than equal to 0. So we have to work harder, right? But nice thing is V is this half this thing, and then it's always decreasing. So V is certainly bounded in the sense that basically all E's are bounded, okay? And since A is negative and then U let's say hopefully is a bounded input, so we can actually conclude that X is going to be bounded. If X is bounded, Ex is bounded, so X hat is going to be bounded, and A is a constant, B is a constant, so EA is bounded, EB is bounded, so A hat and B hat is bounded. So what we conclude from all this is basically all the variables that we are dealing with, X, X hat, A hat, A, B, B hat, and U are all bounded. And so when they are bounded, and then derivatives, their derivatives are also bounded. In this particular case, Ex dot is bounded, right? So since Ex is bounded and Ex dot is bounded, we know that the limit is basically going to 0 from the result that we just saw. Okay, so that's how one can show that. So the limit of Ex is going to be 0, but we can only prove that Ea dot and Eb dot is going to be 0, right? Unfortunately, that just shows basically A hat goes to some constant but not 0, right? B hat also goes to a constant but not 0. How do I know that? Ea dot is nothing but A hat dot, right? So A hat and B hat are going to constant, but not necessarily to the same value as A and B and things like that. So what we wanted to show was A going to A and B going to B and things like that, but we ended up only showing that X is going to X hat is going to imitate estimate. So we started with the hope that basically we can actually estimate A and B through this technique, but we ended up only showing estimating X hat, which is most of the time good enough, right? There are results that show that if we pick U in certain way, then we can actually guarantee A hat goes to A and things like that, and it's quite a complicated topic and things like that. There are other ways of doing the same thing. Instead of picking X hat model to be that, we can actually pick some reference model, and then we can do that, and you can take a look at something like that. Now let's get into controls, right? So in the control case, basically, I'm going to simplify the questions here. Suppose you have X dot equals Ax plus U, where U is the control input. A is unknown, right? But it's a constant. So therefore, no matter what, you will find a case such that A plus K is less than 0. Suppose A is 3, then K can be minus 4, and 3 minus 4 is minus 1, and therefore less than 0. So no matter what the value of A, you can always find K such that A plus K is less than 0, right? So that's the nice thing about it. So if I knew A, and there is such a case as that A plus K is less than 0, I could actually pick U to be Kx, and then that's it, we are done. We are done in terms of stabilizing this thing. The problem is we don't know A, right? In the robust stability case, if we knew A is between, say, certain numbers, and you would take the worst case, so to speak, and then basically for that worst case you take K, and then that works, right? But that has performance issues, because you're trying to control a problem for a range of values of A, and obviously therefore it's not going to be optimal in some sense, right? Though you can actually still optimize certain measure function things, performance measures and things like that, but it's not the best thing to do. If it is possible to actually get a better controller by kind of estimating A, if you knew A, you would get an optimal controller K, right? That's at least the idea behind this adaptive control idea. So the problem is basically identify a strategy to achieve xt going to 0. We don't care about anything else actually. We don't care about A, so to speak, though we would like to have A simply because we can optimize over K's and things like that. So direct adaptive control is far easier than the identification problem that we just saw. So all we are doing is this mentally we are instead of estimating A, what we'll do is we know that there is a K that stabilizes the system, and I'm going to try to estimate K rather than A, right? So this is a philosophically very important point for us to understand. So if we are doing system identification, as I said, we want to do system identification for the sake of understanding what's the future of that particular system. So the parameters, specific parameters, are not as important. So if we can get an estimator, that's more than enough to understand the system. Similarly, if you're going to try to control and you happen to not know exactly what the values of the model, doesn't matter if we have a way of somehow figuring out the parameters for the control, right? So adaptive control essentially estimates the control parameters through some update law and shows that x of t going to 0, and then that's why it's really a beautiful technique. And the extension of that is, you could actually, if there is a stabilizing controller, it will be some kind of function over the states, and then basically any function can be approximated to a neural network, and therefore you can actually search for that weights of the neural network and then hopefully stabilize the system. So that's the kind of the ultimate extension of this direct adaptive control. And I would say these days, if anybody is trying to use learning techniques, basically essentially that's the philosophy that everybody follows. I'm going to basically learn what should be the stabilizing controller, right? If we understand what is stability and things like that in each of the scenarios, then we can do that, right? The result is basically something like this. If I pick u of t is equal to some k hat times x of t, this should be k hat of t. Where k hat is supposed to be estimate of k, and then how is the estimate updated? K hat dot is equal to minus x square t. It's coming from the state. Then what we can prove is limit xt goes to 0, and then the proof is based on this Lyapunov function. I'll show you in a second, and the technique can be extended to model reference adaptive control, which we will state later, right? So let me show you some of the details of the proof. So what I have here is x dot equals a x plus u, right? And I know that there is some k such that this is true, okay? And I'm going to basically assume u equals k hat of t times x of t. In my mind, basically this k hat is approximating k, and then that would stabilize the system, right? At least that was the original kind of idea when they introduced adaptive control, but as I said, without stability it could be very dangerous. So the idea is basically we are trying to estimate this k, and u is going to be k hat times x, where k hat is going to be updated through some particular law, and then we'll put a question mark and then replace it when we know what it is. And I'm going to consider basically a Lyapunov function of the form v of x comma e k. So v of x comma e k is going to be something, but e k, let's remind ourselves, it's basically the error between the estimate minus the parameter that we are trying to estimate, right? So and then we'll pick something like half x square plus, I don't know, alpha by 2 ek square, right? And take the So the closed loop system we are dealing with is basically x dot equals ax plus k hat dot x, okay, and then k hat dot ek dot actually. ek dot is equal to question mark, right? So rest of it is unimportant. So for this particular system, we are trying to show hopefully Lyapunov stability and things like that. So v dot is going to be equal to x dot plus alpha ek dot, right? But x dot is x dot is ax plus k hat, this thing. So plus k hat x square plus alpha ek dot, and I can add and subtract k, and then when I subtract I'll get ek x square plus alpha ek e dot k. That is going to be equal to plus ek times ek dot alpha plus x square, right? So I can pick my ek dot so that this is going to be 0. So I'll end up with a plus k x square is less than 0 for all x not equal to 0, right? So here, so I'm going to replace this question mark with let's pick alpha equals 1. So I'm going to get minus x square, right? So this system in some sense still has this external input k hat, okay? So again, using the same technique as before, we can actually show that x goes to 0, right? And first we convince ourselves that every one of these variables is bounded. How do I know that? V is going to be less than or equal to 0. It starts somewhere. So therefore, basically x is going to be bounded, ek is going to be bounded. But ek itself is away from k hat, from some k. So since k is constant, k hat is going to be bounded. If k hat is going to be bounded, essentially all the variables are bounded. So much more, the e dot k is bounded, so x dot is going to be bounded, all of them bounded, and then basically we can therefore show x is going to go to 0, right? So I mean, if you recall, basically the integral part is going to be less than infinity and things like that. So we conclude that x of t is going to be 0, right? So like I said, this is a technique where we just are interested in x of t going to 0, but sometimes we may want to actually follow a reference, and then that as part of this model reference adaptive control. We will look at that probably next lecture. There's another way of doing adaptive control where we saw how to estimate the parameters, right? Once we know how to estimate the parameter, we use that parameter and we use the value of that parameter, and then perhaps design a controller for that and then control it, right? It's sort of a more difficult technique, but this was indeed discovered probably earlier than direct adaptive control. But for the sake of completeness, how it looks, we will look at it. So let k be some negative number, and we'll see in a second. Identify a strategy to achieve the same thing, right? So what we are saying here is I'm going to pick my u of t to be minus a hat plus k times x hat of t, right? What is the logic behind that? A hat perhaps is going to be equal to a, okay, and then therefore that part is going to be cancelled, and then k is less than 0, k times x. So I'm going to get x dot is equal to minus kx, or sorry, plus kx, where k is negative. So this is kind of similar to that feedback linearization idea that I was talking about. I have something nonlinear, I don't know what to do with it. I'm going to cancel that first and then put some stabilizing controller. So I'm going to cancel ax, which I don't know what it is. I'm going to cancel it through this estimator minus a hat, but then I'll add this k times x hat, right? So So like before, basically we have an estimator x dot equals a hat times x plus u. There's a slight difference from the previous one, but otherwise we can, since we can pick the estimator equation however we want, we will pick that. And then this update law a hat dot is basically given by this ex times x with a minus, and we can conclude that x3 goes to 0, and basically the proof I'm not going to show you again, but basically the proof is essentially going to come from this Lyapunov function and then the technique that I showed earlier, right? Again, this also can be extended to model reference control, right? So again, I mean, I show it to drive the point of basically one can, I mean, this is an important philosophical difference. We can actually have a model, we estimate the model of the system, open loop system, and then try to basically figure out what should be the best way to control that using the estimated values of the model, right? The direct derivative control is, far simpler in its idea. Okay, I know that there is a controller that stabilizes the system, and then I'm going to just estimate that particular controller. And in both cases, we need to understand that there is a controller that stabilizes the system. Except in the second case, basically, we assume first how to estimate it and things like that. So the LQG controller, for example, one way of looking at it is estimate the state through output. So you actually estimate kind of the model and then basically then use it in feedback control. So it's follows similar idea, but it's not necessary when we have more direct technique called direct adaptive control. Okay, so that brings to end of this particular lecture. The next lecture, basically, we will look at some numerical examples. We need to understand how to demonstrate these things, and then we will also look at a generalization of some of these results. Thank you.